Consider this inference. If S, then P prime, P and not Q and not R. If not Q, then S, thus R and P prime. Is this inference valid? We can use a truth table to figure out the answer, but there are 5 different atoms appearing in the argument, so the truth table would need to have 2 to the 5th or 32 different rows. We could use some shortcuts when filling out the truth table to make it a quicker process, but it would be nice to have an alternative method for determining whether the inference here is valid, especially because we won't be able to apply the truth table method at all when we start working with arguments spelled out in more sophisticated formal languages later in the course. So now we'll develop a different method for assessing the validity of arguments, one that we will be able to use later. So how does this new method work? Ordinarily, when we want to demonstrate that a conclusion follows from some premises, we often do that by showing that there's a series of valid inference steps that take us from the premises to the conclusion. And that's essentially how this new method works. So what we do is we introduce some rules of inference, as we call them. Each rule specifies a type of inference that you are allowed to make. For instance, one rule says that from a conjunction, you are allowed to infer either conjunct. Another rule says that from the double negation of a formula, you are allowed to infer that formula itself. Then, if there's a way to get from the premises to the conclusion just by making inference steps that are allowed by the rules, that means that the conclusion follows from the premises. If there isn't, then the conclusion doesn't follow. Now, in order for this method to work, it's important that we choose our rules very carefully. For example, I mentioned that one of the rules allows you to infer either conjunct from a conjunction. Well, suppose we had a rule that said, from a disjunction, you can infer either disjunct. In that case, our rules would allow us to derive conclusions that don't actually follow. For example, from the premise P or Q, P does not follow since obviously it's possible for P or Q to be true without P being true. That happens whenever Q is true and P is false. But if we had a rule saying that from a disjunction, we are allowed to infer either disjunct, then we'd be allowed to derive P from P or Q. So then we'd be allowed to derive a conclusion from the premise P or Q, namely P, that doesn't actually follow from that premise. So we make sure to choose our rules so that that doesn't happen. That is, we make sure to choose our rules so that whenever we derive a conclusion using our rules, the conclusion that we've derived really does follow from the premises that we've derived it from. In the terminology that logicians use, that makes our system of rules sound. In this course, you'll have to basically just take for granted that our system of rules is sound. Rigorously proving that it's sound is something that you would do at the next level up in your study of logic. Now, let me make another point about how we have to choose our rules of inference carefully. Suppose that the only rule of inference that we had was that from a conjunction, you can infer either conjunct. In that case, whenever you derived a conclusion using our rules, you could rest assured that it really did follow. You can't go wrong if you're just deriving the conjuncts from conjunctions. However, if that was our only rule of inference, you wouldn't be able to derive very much. There would be a lot of times where a conclusion did in fact follow from some premises, but you couldn't derive that conclusion from those premises using our rules. For example, from if P then Q and P, Q follows. But if all that our rules allowed you to do was to infer the conjuncts from a conjunction, our rules wouldn't allow you to derive Q from those two premises. So we also have to choose our rules so that that doesn't happen. That is, we have to choose our rules so that anytime a conclusion follows from some premises, the rules allow you to derive that conclusion from those premises. In the terminology that logicians use, that makes our system of rules complete. And that our system of rules is complete in that sense is another thing that you'll have to just take for granted during this course. Rigorously proving that our system of rules is complete is also something that you would do at the next level up. Now, so far, I've just mentioned 2 of the rules of inference that are a part of our proof system. By the end of the course, there'll be 17 rules in our proof system, which may sound daunting, but we'll introduce the various rules in stages. Let's go through one example to illustrate the proof system in action. I'll introduce a couple of more rules along the way. So let's go back to this inference. If S, then P prime, P and not Q and not R. If not Q, then S, thus R and P prime. In fact, the premises here do entail the conclusion. To confirm that, not with a truth table, but by using our proof system, I start by writing down the premises. I number them, I draw a horizontal bar underneath them, and I write them against a vertical line, which I continue some ways down the page. The idea is that these premises are my starting point, and then as I proceed, I'll be drawing further conclusions from these premises. I'll write those further conclusions down here underneath the premises with the goal of eventually arriving at the ultimate conclusion, which in this case is R and P prime. To remind myself that that's the conclusion that I ultimately want to arrive at, I can either write it at the bottom of the vertical line, leaving some space for the reasoning that I'm going to use to get me there, or I can write it off to the side. In this case, I'll just write it at the bottom. So now I have to get to that conclusion from the premises, but only by taking steps that are allowed by the rules of the proof system. We've introduced just 2 rules so far. The rule that says that given a conjunction, you can derive either conjunct, which we call the conjunction elimination rule, and the rule that says that given the double negation of a formula, you can derive that formula itself, which we call the double negation rule. Let me introduce 2 more rules, both entirely straightforward. The first says that given a pair of formulas, you can derive their conjunction. We call that the conjunction introduction rule. The second says that given a conditional and its antecedent, you can derive its consequent. That's just modus ponens. Now, the conclusion that I ultimately want to arrive at in this case is the conjunction R and P prime. If I'm able to derive both conjuncts separately, so both R and P prime separately, then via the conjunction introduction rule, I'll be able to derive their conjunction. So I'll tentatively write down R and P prime here just to indicate that these are now my immediate goals, in the sense that those are the conclusions that I'm now focused on deriving. Now, how might I be able to derive R and how might I be able to derive P prime? Let's start with R. Well, note that not R appears as the second conjunct of the premise at line 2. That gives me a pretty easy way to derive R, because from a conjunction, I can derive either conjunct. So from line 2, I can derive not R. And then from the double negation of a formula, I can derive that formula itself. So from not R, I can derive R. So now I have a plan for how to derive R. I'll write those steps down officially in just a moment. But first, let me think about how I might derive P prime. Well, let's note that the first premise is if S, then P prime. So I know that if I can somehow derive S, then I can use modus ponens to derive P prime. Can I derive S? Well, the third premise says that if not Q, then S. So if I can derive not Q, then I can use modus ponens to derive S. So now the question becomes, can I derive not Q? Well, take a look at the second premise. The first conjunct of that premise is P and not Q, so I know that I can derive P and not Q from that premise using conjunction elimination rule. And then P and not Q is, of course, itself a conjunction whose second conjunct is not Q, so I can use conjunction elimination again to derive not Q from P and not Q. So now I have a way to derive not Q which will allow me to derive S, which in turn will allow me to derive P prime. So now I have a plan for deriving both R and P prime separately, which will allow me to derive their conjunction, which is the ultimate goal. Now it's just a matter of writing out all the steps. So let's start with the derivation of R. First, we derive not R from the conjunction at line 2, which is allowed by the conjunction elimination rule. Next, we derive R from not R at line 4, which is allowed by the double negation rule. Now let's do the derivation of P prime. First, we derive P and not Q from the conjunction at line 2, which is, of course, allowed by the conjunction elimination rule. Then from that conjunction, we derive not Q itself, which is, again, allowed by the conjunction elimination rule. And if you're wondering whether we could have eliminated one of these steps and just derived not Q directly from the big conjunction at line 2, the answer is no. All that the conjunction elimination rule allows you to do is to derive either of the two conjuncts from a conjunction. The two conjuncts of line 2 are P and not Q and not R. So those are the only things you're allowed to derive from line 2 by the conjunction elimination rule. Not Q is a conjunct embedded within the first conjunct of line 2. It's not itself one of the conjuncts of the conjunction at line 2. Okay, now back to the derivation of P prime. From not Q, and if not Q, then S, we can derive S, that's allowed by modus ponens. And from S, and if S, then P prime, we can derive P prime, which is again allowed by modus ponens. Finally, from R and P prime, we can derive their conjunction, which is allowed by the conjunction introduction rule. So there is a way to derive the conclusion R and P prime from the three premises just by taking steps that are allowed by the rules. The derivation that we just wrote out shows one way to do it. So it shows that the inference from those premises to that conclusion is indeed valid.